Dear students, welcome you all to this thermal engineering lecture series. Today we are going to discuss about thermodynamic air cycles. A thermodynamic cycle is a cyclic process, consists of a series of thermodynamic operations which takes place in a certain order, and the initial conditions are restored at the end of the process. A thermodynamic cycle is a cyclic process, consists of a series of thermodynamic operations. Processes which takes place in a certain order. And the initial conditions are restored at the end of the process. The types of thermodynamic air cycles are Carnot cycle, Stirling cycle, Ericsson cycle, Joule cycle, Otto cycle, diesel cycle, dual combustion cycle. The Carnot cycle is an ideal cycle. It is applicable for heat pumps and refrigerators. Stirling cycle applicable for generators. Ericsson cycle applicable for gas turbine and power plants. And Joule cycle applicable for gas turbines. Otto cycle applicable for petrol engines. And diesel cycle applicable for diesel engines. Dual combustion cycle is also applicable for diesel engines. Now we are going to discuss about Otto cycle in detail. Otto cycle, it is also called the constant volume cycle. The Otto cycle consists of two volume constant volume process and two isentropic processes. Two constant volume process and two isentropic processes. Otto cycle consists of two constant volume processes and two isentropic processes. Okay. The PV and TS diagram, pressure volume and temperature entropy diagrams are for Otto cycle. Pressure P in y-axis, the volume in x-axis. PV diagram for Otto cycle. Okay. 1 to 2 isentropic expansion. 3 to 4 isentropic compression. 1 to 4 to 1 constant volume process, 2 to 3 also constant volume process. And the next temperature and entropy diagram. Let the engine cylinder contain m kilogram of air at point 1. At point 1, the engine cylinder contains m kilogram of air. At this point, pressure, temperature and volumes are P1, T1 and V1. In the first stage, isentropic expansion process, the air is expanded reversibly and adiabatically from initial temperature T1 to temperature T2, as shown in the curve 1 to 2 in figure A and B. In this process, 1 to 2, first stage, no heat is absorbed or rejected by the air. In second stage, 2 to 3, constant volume cooling. The air is cooled at constant volume from temperature T2 to temperature T3, as shown in figure A and B in the curve 2 to 3. In this stage, second stage, heat rejected by the air. So, in second stage, Q 2 to 3 equal to Q2 to 3 equal to mCV into T2 minus T3. Third stage, isentropic compression process. The air is compressed reversibly and adiabatically from temperature T3 to temperature T4, as shown in the curve 3 to 4 in figure A and B. In this process, no heat is absorbed or rejected by the air. In fourth stage is a constant volume heating. The air is now heated at constant volume from temperature T4 to temperature T1, as shown by the curve 4 to 1 in figure A and B. The heat absorbed by the air during this process, Q4 to 1 equal to mCV into T1 minus T4. Now work done equal to heat absorbed minus heat rejected. So heat absorbed mCV into T2 minus T3. So work done equal to heat absorbed Q2 to 3 minus Q4 to 1. Heat absorbed minus heat rejected. So mCV into T1 minus T4 minus mCV T2 minus T3. The efficiency equal to work done divided by heat absorbed. Efficiency eta equal to work done divided by heat absorbed. Efficiency eta equal to work done divided by heat absorbed. So work done equal to mCV into T1 minus T4 minus mCV into T2 minus T3 divided by mCV into T1 minus T4. So from that equation eta equal to 1 minus T2 minus T3 divided by T1 minus T4. So from that 1 minus T3 into T2 by T3 minus 1 divided by T4 into T1 divided by T4 minus 1. Take this as equation 1. We know isentropic expansion process 1 to 2. Isentropic expansion process 1 to 2. T2 by T1 equal to V1 by V2 power gamma minus 1. From that, the expansion ratio equal to, we know R expansion ratio R equal to V2 by V1. Therefore, this equation comes 1 by R power gamma minus 1. So, you take this equation 2. Similarly, isentropic compression process 3 to 4. Isentropic compression process 3 to 4. T3 by T4 equal to V4 by V3 V4 by V3 power gamma minus 1. So, from that equal to 1 by R power gamma minus 1. Hence, compression ratio R equal to V3 by V4. From equation 2 and 3, this one equation 3, from equation 2 and 3, T2 by T1 equal to T3 by T4 equal to 1 by R power gamma minus 1. Therefore, T1 by T4 equal to T2 by T3. Substitute the value T1 by T4, this value in equation 1. Substitute the value of T1 by T4 in 1. Eta equal to 1 minus T3 by T4 equal to 1 minus T2 by T1 equal to 1 minus 1 by R power gamma minus 1. R power gamma minus 1. So, eta equal to 1 minus 1 by R power gamma minus 1. Final equation eta equal to 1 minus 1 by R power gamma minus 1. The efficiency of the Otto cycle. Dear students, if you like this video, share to your friends and subscribe our channel. We will meet in next video. We will discuss about problems in Otto cycle. Thank you very much.